Welcome to the second introductory video for Module 5B. This section of Module 5 introduces a new topic, fracture mechanics. So far, we have assumed that all the materials under consideration in our analyses are perfectly homogeneous and isotropic and free of any defects such as cracks, voids, or inclusions, which could serve as stress razors. In reality, this is almost never the case. In general, all materials contain microcracks too small to be seen with the naked eye. Depending on the ways in which the material has been processed, every machine member has some type of flaw that can become a point of stress concentration. Note the theoretical stress concentration factor, KT, shown on the slide. There are two variables defining the shape of the crack or void. The distance A is 1/2 the length of the crack, and the distance C is 1/2 of the width of the crack. In the stress concentration formula, the half length is divided by the half width. When the half width variable C approaches 0, the concentration factor approaches infinity. At high stresses, a sudden brittle-like failure can occur even in ductile materials. Fracture mechanics is the study of this phenomenon. One of the most famous fracture mechanics failures in modern times was the Boston molasses tank rupture of 1919. On the north side of Boston, there was a huge steel-walled tank that held 2.3 million gallons of molasses. Molasses can be fermented to produce ethanol, the active ingredient in alcoholic beverages. However, as the United States was about to enter the Prohibition era, the demand for this product was dropping and hence the molasses remained in storage. Leading up to the disaster, the temperatures were well below freezing. On January 15, 1919, the temperature spiked to 40 degrees Fahrenheit. Further, a shipload of molasses had been added to the tank the previous day. The new molasses would have been warm for transfer. So you have the mixing of warm and cold fluids combined with thermal expansion on the tank itself. At approximately 12:30 p.m., eyewitnesses reported that they felt the ground shake and heard a roar as the tank collapsed, a long rumble similar to the passing of an elevated train. Others reported a tremendous crashing, a deep growling, a thunderclap-like bang, and a sound like a machine gun as the rivets shot out of the tank. Molasses came pouring out of the tank at an estimated rate of 35 miles per hour. 21 people died and 150 were injured. A 2014 investigation applied modern engineering analysis and found that the steel was half as thick as it should have been for a tank of that size. Another issue was that cracks had formed at the rivet holes. The concept of fracture mechanics barely existed prior to World War II. We had the Boston molasses tank rupture in 1919, and then during World War II, many ships and aircraft failed in sudden, seemingly inexplicable ways. The Liberty ships of that era had particular issues. The SS Schenectady was declared ready for service on December 31st, 1942, but only 6 days later, the hull cracked almost in half. The noise from the rupture was heard over a mile away. In 1953 and 1954, there were 3 fatal crashes of the Comet 1 airplanes. The crashes were found to be caused by cracks growing from the corners of the square fuselage windows. On April 28, 1988, a Boeing 737 suffered extensive damage following an in-flight explosive decompression at 24,000 feet. Investigation determined that failure was the result of multi-site fatigue cracking on the skin panel adjacent to rivet holes at a lap joint. The situation was compounded by corrosion. Fracture mechanics assumes that there is the presence of a crack. If the zone of yielding around the crack is small compared to the dimensions of the part, then linear elastic fracture mechanics, LEFM, is an applicable theory. Crack displacement depends on the orientation of the crack relative to the applied loads. If the loads are pulling the crack open, it is considered a mode 1 crack. If the loads are shearing the crack in plane, it is considered a mode 2 crack. And if the loads are creating a shear tear-out condition, it is considered a mode 3 crack. The stress intensity factor K, not to be confused with the stress concentration factor K sub T, is used to quantify the stress state near the tip of the crack. What we want to determine is whether the crack will remain stable or whether it will propagate. Particularly when there are fluctuating loads, the crack opens and closes based on said fluctuation. Each time it opens and closes, the crack grows ever so slightly. Once the crack reaches a critical size in relation to the geometry of the part and the applied loads, it becomes unstable and will propagate at an extremely fast rate. This is what happened to the Boston molasses tank. It effectively unzipped all the way around the circumference of the tank. For the stress intensity factor to be valid, the crack size must be significantly smaller than the surface on which it occurs. Thus, the pictures shown here are not to scale. Note the dimensions and definitions of crack size. Variable A is half the crack width, and variable B is the distance from the edge of the plate to the center of the crack. This assumes that the crack is not located at the edge of the part, as shown in the lower image. Units of stress intensity are megapascals meters raised to the 1/2. The factor beta is to be used when the crack size is large in comparison to the width of the part or plate. Beta takes into account the ratio of the crack half width A and the distance to the crack B. For a crack at the edge of a part or plate, the value of beta is always 1.12. As long as the stress intensity factor K is below a critical value called the fracture toughness, K sub C, which is a property of the material, the crack can be considered to be in one of the following modes. Stable mode, if the load is static and the environment is non-corrosive. Slow growth mode, if the load is time varying and the environment is non-corrosive. Fast growth mode, if the environment is corrosive. When K reaches K sub C, by reason of an increase in the nominal stress or growth of the crack width, the crack will propagate suddenly to failure. The rate of this unstable crack propagation can be spectacular, reaching velocities as high as 1 mile per second. The factor of safety for fracture mechanics failure is defined as shown on this slide. Fracture toughness generally parallels ductility and increases substantially at high temperatures. Higher strength steels tend to be less ductile and thus have a lower K sub C as compared to lower strength steels. Fracture toughness of a material property varies with grain direction. Identifying the grain direction also depends on how the material is processed. Note how the fracture toughness varies for the same material based on the grain direction relative to the crack plane. Also note the chart uses K sub IC as the toughness variable as opposed to K sub C, which is used in our textbook. That will do it for this video. In class, we will work through some fracture mechanics problems together.